So, in the SR latch we have seen that the combination 1 1 we have said that this is illegal. So, why is it illegal? So, suppose we give this particular value say sorry if we give this particular value say 1 1, then you see by since these are simple NOR gates. So, you will get straightway 0 0 there fine. Now, suppose after giving this 1 1. So, we change these 1 1s to the values 0 0, we change both of them to 0. Okay. So, we number these gates as gate number 1 and gate number 2. Okay. Now, what happens is that, so suppose this gate number, so what is the so this is I have applied 1 1. So, this is 0 0 and then I am applying here 0 0 and this is gate number 1, this is gate number 2. Now, suppose suppose I am looking into gate number 1, then what happens is that if both the inputs are 0, as a result this output becomes 1 and then this lower gate. So, this one input is 0, another input is 1. So, NOR gate. So, this value remains at 0. So, it says that after the pattern 1 1, if I so 1 1 gives me the 0 0. After that, if I apply the input pattern 0 0, I am getting the pattern 1 0, but is my answer correct? Okay. So, to see that, so let us now consider the gate number 2 first. So, this was at a value 0 0, both the outputs were at 0 and then we consider gate number 2 first, then getting 0 0. So, this will make this one as 1 and getting this 1 and 0. So, this will make this one as 0. So, that means another possibility is from 0 0 it can also give rise to 0 1 and that is the problem. That is the problem. You see if you apply 1 1 once, okay, then after that if you whatever pattern you will apply. So, this gate number 1 and gate number 2, so they will race with each other, whichever gate makes the transition fast and accordingly the output will be determined. So, you see that in case of this gate number 1 and gate number 2, so physically they are made on the silicon. So, they are not exactly of same speed. Okay. So, what will happen is that one of them will be faster than the other, but we do not know which one is faster. Okay. So, that it is not possible to determine. So, we cannot say which transition will take place first, gate number 1 transition or gate number 2 transition. So, as a result we cannot say whether the circuit will go to the output 1 0 or 0 1. So, this is the problem and this particular problem is known as the race condition. This particular problem is known as the race condition, as if the two gates 1 and 2 they are racing between each other to make the transition first. So, whichever gate wins, so sets the output to 1. Okay. So, that is the problem. Now, with this, so that is why whenever we are using SR latch, so we should be careful that we do not apply this pattern 1 1 to it. So, if we apply 1 1, both the outputs will become 0. So, that part is fine, they both of them are strong zeros, but after that the circuit behavior will become unpredictable. So, as the gates will start racing between each other to make the transition. So, we should avoid giving 1 1 to SR latch. So, there is we can think about some enable signal. So, they are known as gated SR latch. So, to be able to control when the S and R inputs of SR latch can be applied to the latch and thus change the outputs and extra input is used. So, this is the enable signal. So, this if this enable, you can understand that if this enable is equal to 0, this if the enable is equal to 0, then both this S and R. So, these AND gates are getting 0. So, in case of AND gate, in case of SR latch, so if you give 0 0, you see the circuit output does not change. So, the Q and Q bar they hold their previous values. So, if I have this enable line, so if this enable line is 0, so whatever values we give to S and R, so these two inputs will get 0 0, as a result Q and Q bar will maintain their previous values. Whereas, if we take this enable signal to be equal to 1, if we take this enable signal to be equal to 1, then this S and R whatever values are coming. So, they will be coming to this S and R input, and accordingly the circuit behavior will be determined. So, we can say that a detailed truth table can be like this. So, when enable is 0, S and R being 0 0 0 1 1 0 or 1 1. So, they will maintain the previous value q, and whenever this output is equal to whenever this enable line is equal to 1, then the behavior will be determined by the determined by this S and R inputs. Okay. So, for example, in this particular table, so you can say that this whenever this enable is equal to 0. So, this will be holding the q value. So, function is equal to q, and then whenever it is 1 0 0, then you know that the SR latch it does not changes its state. So, that is equal to q, and this 0 1. So, this is this function is basically enable dot q, okay. Then dot S bar R bar, and then this function is again this is setting the resetting the q output. So, this is equal to 0. So, we can say, so this is output is the combination is enable, then S bar and R, and this whole bar, because the output is 0 in this case. So, this way you can write down this truth table, or you can just make a Carnot map and try to figure out what is the function realized for this particular case. Okay. Next, we will look into another example. Say this SR latch, how will it look like? So, I will urge you to finish this diagram. So, as it is said that we can say this initially this q output is low, and here this S signal is going high. So, when the S signal is high, the q output will be high, and then it will after that S signal goes low, this S and R both are 0 0. So, 0 0 means it will continue holding the previous value, and then the R signal is going high. So, as a result, so this will become low. Okay. So, this remains low, and then both of them are low. So, it will remain low. Then this R signal is again going high. So, it continues to be low till this S signal becomes high. So, at this point the S signal is high. So, this is going high, and again, so this will continue to be high till this R signal is becoming high. So, at this point R is high. So, this will be reset, and then this will continue to be reset, and then again at this point the S signal is high. So, it will be going high. So, it will continue being high because S and R both have become 0. So, this way you can trace through this diagram. So, similarly in this case everything remains same, only thing is that the enable line also has to be considered. So, at this point the enable is high and set is high, as a result the signal will become high, and after some time, so enable is high up to this point. So, till this point whatever changes are occurring in S and R, so they will be considered. So, it will come up to this point, then it will go down, then again the S signal is high at this point. So, it continues to be going like this, and then but at this point it cannot change because enable is low. So, next enable is high at this point. So, up to this point the signal value q value will be low, and then when the enable is high, the set line is going high at this point. So, this will become high, and then again it will be then after some time enable has become low. So, it will continue like this, and till at this point enable signal has become high active again, but here the S signal is again high. So, it continues like this, and then after this point enable signal is becoming low. So, it will continue like this. So, this way you can try to draw the diagram for this timing diagram for this this SR latch operation. Okay. So, you just need to follow the truth table. Next, we will be considering another latch which is known as the D latch. So, D latch, so essentially it this logic symbol is like this. So, it has got two inputs, one D input and one enable input. whenever this enable line is high, whatever is coming in the D input will be copied onto the Q, and Q bar is definitely the complement of that. So, you see whenever enable is low, enable is 0, this Q plus remains holds the value of Q. So, it does not change, but when this enable signal is 1, then D whatever, so irrespective of the value of Q, the value is copied onto Q plus. So, it does not depend on the previous Q value. So, it copies this D value to this, otherwise it will be remembering if the enable is low, it is remembering the previous value of Q, but if the enable is high, so it is copying the current D value to the Q value. So, it is going like this. So, this particular latch, this D latch can be realized by just connecting an inverter between S and R inputs of this SR latch. So, you see that in case of in this case what is happening is that if I apply a, so enable I am taking as permanently 1. Now, if I give D equal to 1, then what will happen? So, this S will come as 1 and this R will come as 0. So, as a result this Q output will be set to 1 and Q bar will be set to 0, that is from the behavior of SR latch. Now, if I put D equal to 0 when this enable equal to 1, then this is 0 and this is 1, and by the behavior of SR latch we know that it will reset this Q output to 0 and Q bar to 1. So, you see if we make an SR latch and we just connect an inverter between this S and R inputs, so we get the D latch. And here of course, there is no race around condition, because in the inner SR latch, so it never gets this both S and R inputs as 0. So, both S and R inputs as 1. So, as a result the race around condition is not there. So, you can again finish off, you can complete this truth table for the SR for the D flip flop, not doing it. Now, another interesting type of latch that we have is known as the JK latch. So, in case of JK latch, what is done is that it is a 2 input it is a 2 input circuit. So, J and K, these are the 2 inputs, okay, and it has got a third enable input. So, when this enable line is 0, by our definition we know that whatever be the values of this J and K, so it will continue to, the latch will continue to hold the previous value of Q, but when this enable line is 1, then the behavior of the system will get affected. How? So, this is one way to ensure that S and R inputs cannot be at logic 1 simultaneously, is to cross connect Q and Q bar outputs with the S and R inputs through AND gate. So, what is done? This Q bar line is taken back and it is fed as an input to this AND gate. So, this AND gate, it has got 3 inputs now, J, Q bar and enable, and then this K, it has got inputs like this Q, this Q line is coming here. So, K, Q and enable. So, these 3 are put into this AND gate and they are put into this SR latch input. So, the type of latch that we get is known as the JK latch. Now, otherwise, so when there is a behavior is almost similar to the SR latch, like if I have this say J equal to 1 and K equal to 0. So, what will happen is that this R input will be equal to 0 and then this Q bar line is coming here, Q bar line is coming here. So, this gets the Q line. So, Q may be equal to 0 or may be equal. So, this is the previous Q. Okay. So, this is the previous Q. So, this Q. So, if I write it as Q plus and Q bar plus that way. So, what happens is that, so this previous Q bar was coming here. So, that is ANDed with J equal to 1. So, it get a previous Q value coming here. Now, this Q, there are two possibilities, this Q may be equal to 0 or this Q may be equal to 1. Now, if this Q is equal to 1, in that case this S input is 1 and R input is 0, as a result this SR latch will be set. So, this Q plus will become equal to 1 and Q bar plus will become equal to 0. On the other hand, so if it is if the Q value is equal to 0, if the Q value is equal to 0, then what you are getting is, you are getting a 0 here and a 0 there. As a result, this q it will be maintaining its previous value. So, you see that when this j input is 1, so this when this j input is 1, then if this q value is 0, if the q value is 0, then it is going to, sorry, here it is q bar is coming. I will just explain it once more. So, I said j equal to 1 and q equal to k equal to 0, and this so this q bar line is coming here. So, this q bar line is coming here. So, this q bar can be equal to 1 or can be equal to 0. This line is 0, there is no problem. Now, if this q bar line is equal to 1, in that case this q line was previously it was 0, q bar line was 1. Now, because this is SR latch and this q input, this S input is equal to 1. So, this will set it to 1 and this will go to 0. On the other hand, if this q bar line was 0, okay, that means this q line was equal to 1. So, it will continue to hold the value 1. So, since I am getting a 0 0 here, so it will continue to hold the value 1. So, in case of JK flip flop, what JK latch, what happens is that if you give this j and k, j inputs as 1 and k input as 0, then irrespective of the previous value of q, the new value of q becomes equal to 1. And you can also trace the other way, that is, if the k value is k is made equal to 1 and j is made equal to 0, then irrespective of the previous value of q, so it will become equal to 0. So, q plus will become equal to 0. So, that way it is behaving more like SR latch, but only thing is that racing condition cannot occur, because the illegal combination cannot be applied. Of course, there is another issue, like if I make this both this j and k equal to 1. So, I make this j and k both of them equal to 1. So, what happens is that this q line comes here. So, q line, the previous q value will be coming here and the previous q bar value will be coming here. Now, suppose q was equal to 0, q was equal to 0. So, this is equal to 0 and this is equal to 1. As a result, this line will become 1 and this line will become 0. Okay. Now, you see that after that what will happen? After that this 0. So, I had q equal to 0, q bar equal to 1. From there it has gone to a situation where q equal to 1 and q bar equal to 0. Now, then what will happen? This 0 will be coming back here. So, this will make it 0 and this 1 will be coming back here, will make it equal to 1. And by the SR latch property, next time what it will do? It will make q equal to 0 and q bar equal to 1. It will reset the latch, and so it will make q equal to 0 and q bar equal to 1. So, what is happening is that this will go on happening continually. So, if this, as long as this enable line is equal to 1, if j and k both are made high, then this this latch, so it will go on toggling the state. So, once this once it will be equal to 1 0 and then it will become equal to 1, and that will happen continually. So, this is explained in these two rows, like if this enable is 1, then if j and k both are 1, then if the previous value of q is 0, now the value will become 1, and since the enable is 1. So, now what will happen is that this 1 will come here, as a result it will again change to 0. So, the q line will continually flip and this q bar line will also continually flip. So, this is the problem with the JK latch, that as long as this enable is equal to 1, output will be unstable. So, this j and k inputs are both 1, then q output will change state for as long as the enable equal to 1, and thus the output will be unstable. The problem can be avoided by ensuring that enable is at logic 1 only for very short period of time by using some edge detection circuitry. So, this type of if the problem with this circuit is that is, as long as this enable signal is high, so it is thus whatever values in j are coming in j and k, so they are taken into consideration. So, if we can do something so that this enable is not high for a significant amount of time, only for a very small amount of time it is active. So, we go from this level triggered circuit to edge triggered circuit, then for the edge triggered circuit this type of problem will not occur. Anyway, we will see that. So, the latches are also called transparent or level triggered flip flops, because the change in the outputs will follow the changes of the inputs as long as the enable input is high. So far what we have seen is that we have got, if this is whatever SR latch, SR D, JK, whatever it is. So, we have got an enable line, and we said that as long as this enable signal is high. So, as long as this enable signal is high, whatever inputs are coming, so that is going to affect the output. So, this type of sequential circuits, so they are known as latches or transparent or level triggered flip flop. So, these three terms are synonymous: latch, transparent flip flop and level triggered flip flop. So, these three terms are synonymous. So, latch, transparent flip flop and level triggered flip flop. So, these three terms are synonymous. On the other hand, so if we have some edge triggering. So, edge triggering means this clocks, this enable line or clock line, whatever you call it. So, we put a hat at the triangular shaped structure at the beginning, and then whatever be the input, so that is coming. So, this is input output. Now, this is so this means that we will be considering the input changes only at the edges of this signal. Okay. So, the whatever you call it, so normally we call it a clock signal. So, this whenever these clock edges come, so they will be considered. So, you can make, we have got also symbols for this low level triggered and falling edge triggering. So, low level triggered. So, this is represented by a diagram like this. This enable line, we put a bubble at the end. So, that is the low level triggered. Similarly, for this falling edge triggered flip flop, so this clock signal is shown like this. The clock signal is shown like this. So, that is a falling edge triggered, okay. And whereas this one is a rising edge triggered. So, this type of notations are used for to distinguish between different types of flip flops we have. Next, we will look into how to detect the edge. So, we have said that okay, I want to detect the edge, but how to detect it. So, edge detection circuits, they are used to detect the transition of the enable line from logic 0 to logic 1 or from logic 1 to logic 0. So, it can be done like this. See, suppose I have got this enable signal and we put an inverter and AND these two signals. Then what will happen if this is the enable signal, it is it was low for this much time, now then it is became high and then again it is low. So, you want to detect this situation, that when the transition occurred from low to high. For detecting that situation, we put an inverter. So, due to the delay of the inverter, this En bar signal, so this will be delayed by some amount of time. Okay. So, this is delayed by this much of time. Now, if we take this AND gate, then what will happen, this so this output of the AND gate will be high only for this small amount of time. So, this is not if you consider the delay of the AND gate also. So, you see that for this period of time, both the signals are high. Okay. So, that will be coming to the that comes to the output of the AND gate. So, so that corresponds to this much time, and it is slightly time shifted, and that delay from here to here. So, this is due to the delay of the AND gate. But anyway, so by using this circuit, so I can detect the precise time at which this transition has occurred from low to high. Similarly, if you are going for to detect high to low transition, then we can make the circuit like this. So, this enable line is inverted and there is another inversion. So, that comes like this, and then if you go on doing this ANDing, you will see that ultimately it will land into a pulse on this line, when which actually corresponds to this transition, this high to low transition. Okay. So, this corresponds to this transition. So, this way we can use this digital gates to realize this edge detection circuits, and then use that use this En dash signal as the edge triggering clock signal for the flip flops. We will next look into edge triggered JK flip flop. So, this edge triggered JK flip flop. So, as I said that edge triggering can be positive edge triggered or negative edge triggered. Now, you see that this circuit is otherwise similar to whatever we have seen. This previously we this name of this line has changed from enable to clock, otherwise the lines are same. So, previously, so this line was drawn directly and connected here. Now, we have put a small edge detection circuitry before this. So, that way we are we have done it like this. Now, what happens is that this only during the time for which this line is high, and that precisely happens when the clock is making a transition from high to low. So, only when this it is making a transition from high to low, sorry, when this transition is low to high like this, then only this output will be equal to 1, and then only this j and k values will be allowed to come to this s and r. So, whenever this clock is high or clock is low or clock is making a transition from high to low, so this output at this point will be 0, as we have seen in the previous slide. So, you see that when only when this was making a transition from low to high, so this pulse came, otherwise this en dash line was always 0. So, this falling edge was not detected here. So, that is why, so if it is a falling edge or a high level or low level of the clock signal, irrespective of the values of j and k, this q will maintain its previous value. Whereas, if there is a rising edge like this, then this depending upon the value of j and k, this the q value will change. So, it will be becoming equal to 0 or 1, or either it will maintain its previous value or it will be changing. Now, because of this edge triggering, so we cannot have the this toggle, because this by the time this if the toggle has to occur, then this clock has to appear again, this clock transition has to appear again, and for that we do not bother, because in the previous case what was happening is that you will be depending upon the delay of this JK flip flop, depending upon the delay of these gates. So, this S and R settings were being done. So, what was happening is that, so if this j is high for this much of time and k is high for say this much of time. So, during this time this q output will be continually changing like this, q output will be continually changing like this. So, why this thing happens? So, this particular delay is equal to the delay of these gates, this AND gates and all, okay, and this the NAND gates or NOR gates that you have inside. So, this is determined purely by the combinational elements that you have in the circuit, whereas for the edge triggered circuit. So, we are not we will be getting this type of behavior, but only at the clock boundaries. So, that is why we are it is much safer. Like here also, if the j and k both the signals are high, if j and k both the signals are high, like say j is high for this much time and k is high for this much time. Now, in between if you have the clock signal going like this, so this is the clock, then the transitions you will see the q output is so at this point the q value will change, if the q was 0, q will change here, again at this point the q will change, again at this point q will change. So, that is determined by the clock boundary. So, it is controlled, it can be controlled externally. By controlling the clock signal, you can control the toggling rate, whereas for the latch JK latch we do not have that control. So, that is purely determined by the delays of the constituent gates in the latch. So, this JK edge triggered flip flop, it solves that toggling problem, and that way it is helpful.